So in this video, what we're going to talk about is kinetics. This is part 4 of a 4-part series on kinetics for General Chemistry 2. And the thing we're going to really focus on today are what we call mechanisms. They're fundamental steps that give rise to the overall equation and help you understand the overall rate mechanism and the overall rate expression. So to get started, we're going to revisit a reaction we had done on an earlier video where we basically are going to take this trimethyl bromide, react it with water, and end up with a methanol or trimethyl alcohol. And so what we learned in that video is there's actually 2 steps. There's an initial step that's actually very slow, which makes this carbocation. And in the second step, the carbocation interacts with the water. It is a quicker step, so this happens very rapidly, and it forms the alcohol. And it goes through this, what we call transition state. So just a couple important things here. These intermediates, they may be isolated, but they are not something you order in a bottle and add as a reagent. Transition states are very fleeting. So when you get the rate expression, you look and you say, okay, rate times K times the reagent. The expression is based on just the slow step, and that's always the case for kinetics. Now, the overall rate expression, and so this is what I'm going to start with. I'd like for you to understand, if you have a multi-step reaction, if you know the kinetic steps that make the overall reaction, how do you write the overall equation? So let's practice that piece first. So here are the 2 steps. How do you write the overall equation? So basically what you do is you place the steps over each other and you add those equations together. And we've done this in General Chemistry 1 when we did some thermodynamics. So you gather up all the reactants on one side and all the products on the other. But first, if you have something that's common as a product in an earlier step that becomes a reactant in a later step, for example, this carbocation is a product in this first step, and now it's a reactant in the second step, it in essence cancels out. So we can get rid of it, and then anything that's left over you bring down. And then this is the overall equation. Now I might just rewrite this quickly, not that that's a big deal, but when you're doing a balancing stoichiometry, your ionic compounds, you usually put those together. So you might see it this way. This helps with the stoichiometry and balancing. So once again, this overall equation that you've come up with, whether you write it this way or you write it with the ions combined, these are great for doing stoichiometry. These are great for doing thermodynamics calculations. They do not, though, solve your rate equations, because as we learned in earlier videos, the only component out of these steps that determines your rate equation is the slow step, which is in this case is step 1. Consequently, we'll just go through this process here. If I was writing the rates for each step, if it's a single step in a mechanism, you take only your reagents, your starting reagents, and put those in the rate expression. Rate equals the constant times the starting reagent, in this case, trimethyl bromide. So if I was to write the rate equation for the second equation, I'd say, okay, well, there's the carbocation and there's also water. And if we use the same process that we just did, you'd add those together and say, well, the overall rate is these added together. But that's not true in kinetics. That's not true. All you care about is the slow step. Okay, so the rate overall, just like I've shown you up here, depends on the slow step. And that's the real take-home here. If the first step is slow, overall rate is the rate expression for the first step. Another guidepost, something else to think about when you write these overall rate expressions. And that is, you will not put reagents in here that are, as we've learned, are intermediates, or if they're transition states. Those don't end up in rate expressions, because that's not helpful to us, because I can't get an intermediate out of a bottle and add it to control a rate. I definitely can't get a transition state out of a bottle to add it to control a rate. So this overall rate actually has meaning in the lab. It's how much of this trimethyl bromide can I add to determine the rate at which this reaction will flow. Okay, just another thing that'll help you as we understand these steps is just a definition. So let's start with the first step here. This is unimolecular because there's only one molecule. Uni is 1. In this particular step, though, there's the carbocation and there's water, so that's 2 steps. That's called bimolecular. And when you look at the rate expression for that, there's 2 molecules involved, bimolecular. And if you had a third molecule involved, you call it termolecular. This is kinetics terminology, and sometimes it's interchanged with order, because you remember from earlier videos we called this a first order step, and this would be a second order step. And the reaction is first order overall. So let's talk about proposing these steps. What if you're working backwards and you say, well, what are possible steps? And this is a little bit of it's a theoretical construct, but I'll just give you some outline, and if you go on and study more kinetics, I'll get into more details, but I'm just going to give you some just good rules of thumb, some general principles to get you used to this. So what we're going to do is we're going to start with the overall expression. Okay, so once again, this is not an individual step, it's the overall expression. And then I've drawn this picture to help you understand it a little bit. I have A reacting with B and reacting with C to make this complex an ABC complex where these are all combined. So if I was talking about, okay, what mechanism would make sense? First off, the elementary steps must add up to the overall balanced equation. Whatever I come up with for steps, when you go through that process of stacking them, canceling things that are common between reactants and products, getting a net overall equation, the steps have to equal the overall balanced equation that you use for stoichiometry and thermodynamics. When you get done also, somewhere out of those steps, there's going to be a slow step, and maybe this will help a little bit. If I'm reacting A with B, that might be a step that's separate from C from reacting with B, but you can just see this intuitively that A, finding its location into that very specified reactive site, is going to be lower probability than C fitting alongside B, which you could see that if C was to twist around, it'd fit on 2 sides. So this is going to be a quicker step because it's easier to achieve, matching this side or this side. Then the overall rate law is probably determined by this step. And so the steps that you propose need to take account of that. And that's kind of a theoretical thing. So the last step is something that's you should be able to apply in general chemistry too, and that is proposed steps won't involve more than 2 molecules. And let me explain that a little bit. If this, for example, let's just say that we thought this was a step for the equation. Instead of being the overall equation, we said, A, B, C, they're going to find each other simultaneously at the same time. That's a fundamental step. Well, you can think about the probability of that happening. That, okay, A is going to go around and find B, and that has a certain level of probability that will happen. And C finding B, that has a probability of happening. And overall, if that was done in one step, though, you can see that the odds of that happening at the same time, both A and C snapping into place at the same time, now the probability is kind of going off the charts. So what I would say is when you look at individual steps, this termolecular type step or above is getting highly improbable. There are some termolecular fundamental reaction steps. Probability on them is very, very low. But you have 4 molecules or more all colliding and binding at the same time. That's not even a reasonable step. It shouldn't even be proposed in an individual step. So for general chemistry 2, this is a good rule of thumb to follow. Look, if I propose a mechanism step, it's probably 2 molecules at the most, bimolecular. So just a reminder, you have unimolecular situations where something decomposes. You have bimolecular reactions where it's the same thing, there's just 2 of them present. But there's also bimolecular, like what I just demonstrated, was there's 2 different molecules coming together to form a third molecule. And if you look at the rate law, in this case, you can look at the step and use the stoichiometry of it to write your rate law. A coefficient of 1 in front, it's first order. If there's a coefficient of 2 in front, then it becomes second order. Or if it's 2 molecules, then you get 2 molecules here. This still is an overall rate expression that's second order. So let's talk about this. How do you write a rate expression with a reaction with a later, slower step? So here's the fundamental steps that we proposed. Step 1, step 2. It happens that step 1 is faster, and that makes sense when you look at this reaction diagram where it has that lower activation energy, so this happens very quickly. Step 2 is actually the slow step. So now how do you write a rate expression for this? Well, let's start by doing this. Let's just gather and get the overall thermodynamics or stoichiometry expression. Just a good practice again. The NO3 cancels out. You're left with this. So now we're ready to write the actual overall rate law, which we now know is determined by the slow overall step. So if I did the rate of the first step, which is actually not significant because it doesn't determine the rate, but just so I'm going to show you here. You'd write it in. Here's the reactants. They're raised to the first power. Then if you did this, the rate for the second step, here's the reactants. They're raised to the first power 2. There's coefficient 1 in front of them. And we know that this is actually the rate determining step, but there's a little bit of a problem here, and that is that the rate expression uses an intermediate, and that's not anything that we can measure or pour out of the bottle to control the rate of the reaction. So I'm going to show you a trick that basically will show you how to get, the key here is we want to get this NO3 term out of there. We want to express our rate determining step without NO3 in there. So in order to do that, we need to look at the science to understand what math would be appropriate. So let's look at the reaction diagram to understand how this makes sense. Let's just pretend this is like cars driving up a hill. This first step, although it's tough, it happens fairly quick compared to how slow this step happens. So consequently, traffic going up the hill could get set up and establish a bottleneck right here at this intermediate state. And so some of these cars might turn around and go back home, right? So you could actually set up an equilibrium where reactants are forming products at the same rate at which products are decomposing and forming reactants. So some of this NO3 is decomposing back to NO plus O2. That equilibrium gets set up at the same rate because it's being held up here with this higher activation energy hump. So that's one of the keys to getting over this problem we have right here. So let me show you what I mean. We're going to go to the next slide, but I just want you to remember, first step is fast, so this activation hump is below the second step. So consequently, products could be decomposing at the same rate at which they're forming, and that's the key here. So let's go to the next slide. So the assumption I just said is that there's a rate forward that's exactly equal to the rate in reverse. Now what I've done is I've written a rate expression for running this reaction in reverse. Now just to keep it clear which is which, this is a k to the minus 1. We're running the reaction in reverse. It has a constant run in reverse, which would make sense. If the rate forward was some number here, then the rate backwards would be divided by that number. When you run it in reverse, this is actually the reactant forming these products. So when I write the rate expression, I write it that way. But what we've decided is equilibrium is established, so the rate forward is exactly equal to the rate of reverse. Understanding the science will tell us what to do with the maths. So now what we're going to do is isolate this tricky NO3 term out, because that's the intermediate that we can't use. And we're going to say, well, that algebraically is equal to this expression. And the nice thing about this expression is it has two reagents that we can measure. So now we can go back to the slow step, see it right here? And we have a substitution where anywhere that I see NO3 concentration, I can substitute out with this, right? It's a way to re-express intermediates with measurable reagents. It's based on that fact that rate forward is equal to rate backwards when you bottleneck these reactions. Okay, so now we go in and we re-express this thing with this substitution put in place. And now it's all in terms of NO and oxygen. Just collect things down a little bit. And here's a nice thing too. See these three constants here? We can measure those in the lab, so we know that together they're fixed. But if you multiply these two together and divide by the third, you're going to just get this third constant. And then you can collect the NO times NO and get NO squared. And now this becomes a third order overall rate expression. Right? So now we're talking about the overall rate. It does depend on NO and O2, which are two things you can measure. It's first order in regards to oxygen, second order in regards to nitrogen monoxide. And if you took it in the lab and actually did measurements, you could back calculate this K, which we've learned in I think the first or second video. All right, so let's do some practicing. The first thing I'd like for you to do is practice if you have a multi-step reaction. So here we go. Here's a 3-step reaction. Can you stack this up and write the overall balanced equation? Can you determine the molecularity of each step? Is it unimolecular, bimolecular, termolecular? Can you write a rate law for each step? Let's practice writing the individual rate laws for each step. That'd be great practice for you. So at this point, stop your video, get out your paper and pencil, look at this problem, see if you can solve it. And when you're done and you're ready to check your answers, then restart the video. Okay, let's see how you did. So remember, you stack these, and then what we're going to do is, now there's two ways to do this. I'll show you a couple ways. I showed you in an earlier video one way, but I'll show you something else. If you'd like, you can just take all your reactants down and all your products down in just one line. You can get it down here, and then you can start canceling things out. Remember that if products or reactants in another step, right, the equivalent goes away. Or in this case, if you see the same thing on reactants and product side, you can just cancel it. So here, for example, I see chlorine, and I see chlorine here. So we can cancel those with these two chlorine. These are individual chlorine atoms. And then here's that carbocation, and here's the carbocation on this side, carbocation here and here, so we can cancel those two. Now we can just rewrite whatever's left over, and that's the overall reaction. So now this is not a rate law. This is for stoichiometry and thermodynamics. This is the overall equation. So here's another way you could have done it without bringing everything down and canceling things that are on that match between reactants and products. You can do, as I showed you in the earlier part of this video, you can just cancel things that are products on one side that become reactants in the next step. So for example, here I have chloride atoms, and it becomes a reactant in this step and also in this step. So we can cancel those out. And here's that carbocation and the carbocation over here, so you can cancel those out. And now you can just collect everything that survived, okay, the canceling process. And there's your overall expression. Determine the molecularity of each step. The first step has one reactant, so it's unimolecular. The second step has two molecules, bimolecular. The third step is two molecules, bimolecular. So then writing the rate laws for the elementary steps, one molecule here, it's first order overall with the chlorine molecule. The second step is second order overall. It's first order for the chlorine atom and first order for the trichloromethane. Third step, second order overall, but first order for chlorine molecule or atom, and also first order for the carbocation. So here's another practice step for you. What's the rate law for this overall reaction? So now we're not talking about, although you might want to just practice drawing the overall equation, but the goal here is to write the rate law expression. And pay attention that the first step is slow and the second step is fast. So once again, now stop your video, try and solve the problem on your own paper. When you're ready to check your answer, then restart the video. All right, let's see how you did. All you have to do is base it on the slow step in this case, because it's the first step. There's two NO2s involved, so it's second order overall, but all it depends on is the concentration of nitrogen dioxide. Okay, here's another. This is a tough one. Let's revisit the mechanism by which chlorine gas reacts with trichloromethane to form hydrochloric acid and carbon tetrachloride. So this is a three-step mechanism. Here's the overall reaction, but the question is, what would you do? How would you get to the rate law? And this one I'm going to give you a little bit of hint. Here's where you should end up. So if your math is right, you should end up here. So let's see if you can break that apart. And let me help you out a little bit too. Let's just sketch this thing real quick. Here's a fast step, so it has a low activation energy, right? And in the second step, this chlorine atom reacts with this trichloromethane. And this is the slow step, so this is the rate determining step. And then there's this third step where another chlorine atom just comes together and makes a carbon tetrachloride. So before you go to do your proof, let me remind you of one thing. It's a fast first step. So remember, these guys they set up equilibrium. It's a slow second step. So this is the rate determining step. The problem with the second step is that it involves a chlorine atom, and that's nothing that we can truly measure. So we need to get that out of there somehow in your proof. And then the other thing is that third step. Now that might be a little confusing to you, but the nice thing is this. Any steps after the slow step, you don't need to use them in your expression at all. All right, so stop your video, solve the problem on your own paper, and when you're ready, restart the video to check your work. All right, let's see how you did. And once again, keep in mind that somehow we're going to use the fact that this sets up equilibrium in the first step to somehow re-express what happens here in the rate determining step. And we can get this chlorine atom out of there, that little intermediate, that little pesky intermediate that's not going to help us in the overall rate expression. All right, so here we go. Here's the slow step. So if we were to write the slow step overall, we would say K2 chlorine atom times this trichloromethane. So we need to get rid of this somehow. The species is an intermediate, so it needs to be expressed in terms of reactant concentration. And remember the trick. If you go to that first step, K1 times chlorine molecule is going to could be re-expressed as taking the chlorine atoms. There's two of those that could come together and come back to this chlorine molecule. So these are equal because in that first step back on the hump, I'm going to go back and show you that picture right here, right? If I have two of these molecules, they can come back together and form a chlorine molecule, the diatomic chlorine molecule. So this is where the rate forward is equal to the rate backwards. Rate forward is equal to the rate backwards. So we'll go up, rewrite that, say that that is equal to that. So now what we want to do is re-express this guy by himself so that we can use him in substitution up here. All right, so we're going to solve for this. So you can see you need to get the k to the minus 1 underneath. That's where that happened. And then basically, if you want to solve for chlorine squared, you have to take the square root of both sides. So you end up with this expression, chlorine atoms equals this expression here. And so now this is nice because now we have the diatomic chlorine gas that we could add from a gas canister into the reaction. And that substitution can go into the slow step 2 rate expression. But first what we did was we pulled the diatomic chlorine 2 molecule out from underneath the square root. And then we made the substitution. And if you plug that in and collect terms, and then you can re-express that square root in a different form just to clean it up a little bit. And you'll see here's your final rate expression, which has the chlorine molecule raised to the half order, and the trichloromethane is first order, so you actually have 1.5 order overall. All right, so in this rate expression, now you know what really controls the show is the amount of trichloromethane, but chlorine gas does affect it, just not as powerfully as the trichloromethane because of the order. This is first order, this is half order. Remember, you can just re-express all these things because once again, it's a constant. So when you work out these constants, it becomes the new constant, right? We're just going to throw it in as a k. It's just a little simplification that occurs. All right, one last thing to understand in kinetics is something called a catalyst. And this is where my bad Southeast Colorado humor comes into play, and that is, I'm sure that this guy taking delivery on these animals probably has a catalyst. The catalyst is a substance that increases the reaction rate without itself being consumed in the reaction. In general, a catalyst provides an alternative reaction pathway that has lower total activation energy than the uncatalyzed reaction. How does that really happen, though? Well, maybe it lowers the energy for bond breaking forming, or maybe a catalyst just holds something in place. That's what preposition is, to increase the frequency. And by that I mean frequency of collision. So we're going to look at a reaction where you basically add hydrogen across a double bond, what's called a hydrogenation reaction. And consequently then you end up with alkane, where the hydrogen molecule will split up and the hydrogen is added to each side, to each individual carbon on these double bonds. So how does the catalyst get involved? So the catalyst is this rhodium complex, and the thing I would point out about this complex is that it first off binds the hydrogen and splits it. So once again, back to that idea, what does the catalyst do to lower activation energy is it can soften up bonds, because you can imagine in order for this to happen, the hydrogen has to break apart. The rhodium does that for you. It also begins to soften up this carbon-carbon double bond, because one of those double bonds has to go out to form to the new hydrogen. So the rhodium complex goes in here, and then there's this little loop in here which is called hydrogen migration. I'll help you see just a little bit. You don't have to totally understand this mechanism, but the key is this. We soften bonds, we soften the hydrogen, we soften the alkene. The other thing is proximity. The fact that the metal holds these close to each other is in fact like raising the concentration, because basically you have the hydrogen right next door in a molecular space, merely angstroms away from the double bond it's trying to bond to. So, and also orientation. I'm going to just show you that this first off is the rate determining step. So there's multiple steps in this mechanism, but the rate determining step is right here in the hydrogen migration. And in that hydrogen migration, if you look at these double bonds or trying to form new bonds with the hydrogen, if you could really see that in three-dimensional space, this octahedral complex transition state basically that's formed positions the hydrogen, one of the hydrogens, right over the top of one of the carbons that it's trying to form a new bond with. And so that's one of the keys. That's a hydrogen migration. It migrated from off the hydrogen molecule and migrated onto the double bond. So that's one of the transition states. But you can see once again, we got proximity, we held it in position for this to happen, and we also softened up the bond. So this kind of covers the whole gamut of why a catalyst will help things happen. So if we now look at the reaction diagram, you can see if you have a regular reaction, just very simply, A plus B makes the products, and it has some high activation step. If you run it with a catalyst, you might have different transition states, but overall that activation energy is lowered, therefore the rate is faster. So what does a catalyst do? Lowers the activation energy. Catalyst does not show up in the products. It's not used up. It can be reused. So that's another key. And so it doesn't then become part of the rate expression. So the last catalyst I'd like to talk about is an enzyme, because you hear about that all the time in your body. You have enzymes, and this is a biological catalyst, but it's still a chemical function. And I'm just doing this with overall pictures to help you understand. Look, if a catalyst catalyzes the reaction of these two substrates, in other words, the key is that you have these two molecules, biomolecules, that have to combine and form this product. And we can say this product is like some important protein that's used to make tissues, or maybe it's a carbohydrate that's used for fuel. It's just some sort of important biomolecule in our example. And the enzyme in this case holds these substrates in place and prepositions them so that they're able to react to form the product. The other thing is when they bind into this enzyme pocket, then they're obviously closer to each other, so that's proximity, but they're also oriented right. In other words, this end has to connect to this end. So because of the positioning of the enzyme, they are connected correctly. So all of that has to do with lowering the activation energy and increasing the frequency that this reaction is going to happen. So I hope this video has helped you understand the mechanisms behind kinetics.